Okay, in this video we'll be doing a resonance structure example, and our molecule today is H2CnO-, and what we'll be doing is using this rule of electron pushing by either breaking bonds to gain lone pairs, or we can move lone pairs to create bonds. And this will make a lot more sense when I actually do the example. Right here I already have the atoms already spaced out. Here's a double arrow to indicate these are resonances, all enclosed in brackets. What we can do is we can put our minus right here because we know our example is negatively charged, the molecule. So let's draw the Lewis structure. So this is an equation I like to use when drawing Lewis structures, which is the number of bonds equals the demand minus the supply. Our demand is how many electrons each atom likes to be surrounded by to have a noble gas configuration. So hydrogen likes to have a total of 2 because it likes to be like helium. Carbon, nitrogen, oxygen all follow the octet rule, so they have 8. And if you add all those up, that should be 28. Let me clean that up. So our demand is 28 minus our supply. Our supply is how many valence electrons each atom can actually contribute. So if we look at hydrogen is found in group 1, so it contributes 1 valence. Carbon is found in group 14, so it's 4. Nitrogen 5, oxygen 6. Don't forget we need to add a +1 because our molecule is negatively charged and electrons are negatively charged, so we're adding another electron to our molecule, so it'll be +1. If this molecule was positively charged, we'd be losing an electron or losing a charge, so we'd be subtracting it. But once again, it's negatively charged, so add 1. Add all these up, and that should be 18. So divide that all by 2, and we'll find out that the number of bonds we have is 5. Pencil out. First, always connect your hydrogens because they follow the duet rule, and they like to be like helium. They can only have a total of 2 valence electrons. So let's finish off our molecule by connecting all the atoms. Okay, we have 1, 2, 3, 4 bonds. We can have 5, so we must give it 1 more. So let's just give it to the carbon and the nitrogen. And now we must fill in our remaining electrons to finish octets. So I'm going to use these as electrons. So carbon already has an octet. Nitrogen needs an octet. Oxygen also needs an octet. So let me give it some electrons. There we go. Now we must find their formal charges, and we do that by using the formula valence electrons minus lone electrons plus number of bonds, all in parentheses. You may use a different equation, but I like this one because it's quite quick. So carbon is found in group 14, so it's 4 valence, minus the lone electrons, which it has none, there's no lone electrons on it, plus the number of bonds, it has 2 singles and a double, so 1 plus 1 plus 2 is 4. So 4 minus 4 is 0. So carbon does not have a charge. Let's look at the nitrogen. So nitrogen is found in group 15, has 5 valence, minus our lone electrons, which is 1, 2, plus the number of bonds is 1, 2, 3, 3 bonds. 5 minus 5 is 0, so that also has no charge. So we could automatically put oxygen with our negative charge because we already did all these and our molecule has to be negative. So we know oxygen has a negative charge, but let's just do the formal charge just to show it. So oxygen is in group 16, has 6 valence. How many lone electrons does it have? 1, 2, 3, 4, 5, 6. Plus the number of bonds, it has 1 bond. So that's 6 minus 7, which equals -1. So that's where our negative charge comes about. Now, what I'm going to do is redraw this molecule exactly the same over here, so it will make much more sense when I move electrons and it doesn't get really messy. So let's do that. So redrawing it. Single bond here, we need our electrons, so let's do that. Okay, let's move these. I don't know why I put those there. They don't go there. And we put these up here. We cannot forget our charge. Our charge was on the oxygen. Now what we like to do is go from a region where it's negative towards a positive, which we don't have in this case. So we're just going to start moving lone pairs, which I mean up here. So if we're going to move some lone pairs, we're going to be creating bonds. So let's try that out. Let's move these electrons and put them right here to make a double bond. So let's do that. So let me get the pencil out. We now have a double bond here. We just got rid of these electrons because we moved them. Keep in mind, when we move lone pairs, we will also be moving charges. So now the charge is sitting on this nitrogen. But look here, we have 2, 4, 6, 8, 10 electrons surrounding this nitrogen, and we can't have that because it violates the octet rule. So what we need to do is now break a bond. So what happens when we break a bond? We'll be gaining lone pairs on an atom. So let's break this bond to make a single bond and place these electrons on this carbon. So let's do that to make it look neater. Let me get these electrons out. So we have just moved these electrons from that double bond we broke. Keep in mind this is still following over here, so now it's on the carbon, and that is what our other resonance looks like because this molecule is negatively charged. There's a negative over here and a negative over here, so we put our negative right here. So let me just get rid of these. That is what it should look like. Now we need to figure out which is a better representation of our molecule. However, both of these together make up the resonance hybrid, which is a combination of all the resonance structures. But sometimes we have a better molecule that will contribute more, and we call that the major resonance contributor, while the one that doesn't contribute as much is called the minor resonance contributor. So who's the major one? We use these rules below, and octet is always the best, meaning this will always overrule all of these charges, all of these rules. So we have a 2, 4, 6, 8, an octet, 2, 4, 6, 8, an octet, 2, 4, 6, 8, an octet. Okay, 2, 4, 6, 8, okay, 2, 4, 6, 8, 2, 4, 6, 8. All right, they both have octets. Now what? Least separation of charges. Okay, we have a charge here and we have a charge here. So are they equal? Not quite. We have a third rule. Negative formal charge on the most electronegative atom. Okay, oxygen is found here in the periodic table and carbon is found here. Now we know electronegativity increases this way and this way. So oxygen is the more electronegative atom and it has the formal charge over here. This has the negative over here and is less electronegative than oxygen. So that would mean this is the major resonance contributor and this would be the minor resonance contributor. So that does it for that example. I hope this video helped you and have a good day.